Welcome back to ECE 501B. Today we are going to pick up where we left off with the linear dependence lemma, and we're going to re-examine that. But before we get started, just some announcements. Homework number 1 is due on the 5th of September, and homework 2 is due 1 week later. Another announcement is, in addition to this lecture that you will be responsible for, I will probably also put another lecture up on dimension, and that will allow us to conclude chapter 2, and the next time we physically meet, after you've covered this material and the dimension lecture, we'll be ready to start in chapter 3, which is covering linear mapping. So that's where we're headed. We want to, in the next couple of times that you'll be looking at some lecture material, complete chapter number 2. And as a part of that, today let's re-examine the linear dependence lemma and state some consequences of that linear dependence lemma. One of those is Theorem 23 in chapter 2, which that says in a nutshell that the length, if you're given a list of linearly independent vectors, the number of vectors in that list, or the length of that list, is less than or equal to the length of any list of vectors that actually span the set, or span that vector space. So a spanning set of vectors spans the vector space, and that's always going to be greater than or equal to a list of linearly independent vectors, and that's a result of the linear dependence lemma. Another consequence of that is Theorem 26, which is finite dimensional subspaces. If the vector space is finite dimensional, if our vector space V is finite dimensional, then subspaces of V are also finite dimensional, and that should seem rather intuitive because subspaces, in terms of a concept, are like subsets of the underlying vector space. Our focus today will mainly be on finding or creating sets of basis vectors, and if we have a set of basis vectors, then those vectors have two properties. One, they span the entire vector space V, and that set of vectors is linearly independent. And we'll get into that a little bit more as far as what that means, but now you can sort of think of these vectors allow you to get to any location in that vector space, and you can do it by a unique combination of those basis vectors. You can do a linear combination, a unique linear combination of those vectors. In terms of creating basis vectors, we can do it a couple of different ways. We can either do it by throwing away vectors. If we have a spanning set of vectors, we can start, or a spanning list, we can start removing any of those that are redundant, and so we'll create basis by reduction. Or we can grow a set of linearly independent vectors into a set that, in addition to being linearly independent, span the vector space. And so by extension, we can extend a linearly independent list of vectors to create a basis. That's where we want to get to today. To sort of recap where we have been with the linear dependence lemma, if we are given a linearly dependent list, then that we can sort of think of two different ways. One, A, is it is possible to find a vector in that list that can be expressed as a linear combination of the remaining elements, or that means that there's a vector in that list of vectors, if that list is linearly dependent, that is in the span of the other vectors in that list. And the second part is that removing a linearly dependent element from the list produces a new list with the same span as the original list. And that's going back to this throwing things away. We can throw vectors away or remove vectors and not negatively impact that list's ability to span the vector space or to span the same spanning range that was spanned by the original dependent list. Let's look at proving this removal of a element or a vector from a list to generate a new list that has the same ability to span the same space as the original list. To do that, let's assume that we are given a linearly dependent list of vectors. That's just what we're assuming. So that's okay. We can just call that list W, and it's made up of n vectors, v1, v2, up to v sub n. And also, let's assume that we have a vector that is in the span of that list of vectors v1 through v sub n. And let's call that arbitrary vector u. So we're saying, let's assume u is in the span of w, or it can be created as a linear combination of vectors v1 through v sub n. Let's write that down. If we have u in the span of w, that now says that u is equal to alpha 1 v1 plus alpha 2 v2 up to alpha sub n v sub n. And that's for some non-zero scalars, alpha 1 through alpha sub n. Some of those scalars could be 0, but you have to have at least one that's not, if u is in the span of those vectors v1 through v sub n. Now what we want to do is show that we can actually remove a vector from this original list that's contained in the set W. It's a linearly dependent list. We can throw one of those away and still allow that to represent or contain U. And the way that we will do that, let's just go ahead and assume that we have labeled our vectors in such a way, since this list v1 through v sub n is linearly dependent, let's just assume that the last one, v sub n, is the one that can be rewritten as a linear combination of the previous n minus 1 vectors. Let's say then, but we can express v sub n in terms of the other vectors. Again, we're assuming the appropriate labeling of these original vectors v1 through v sub n. Really what we're saying is that we can, if these vectors are linearly dependent, then what we're saying is we can form a1 v1 plus a sub 2 v sub 2 plus dot 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 plus a sub n v sub n, and we can make that sum to 0. If these are linearly dependent vectors v1 through v sub n, we can find some non-zero scalars a1 through a sub n to make this happen. since these are that list is linearly dependent. That means then that we can solve for v sub n, and let's just assume then, and that's what we were assuming, that v sub n was the one that was capable of being a linear combination the previous n minus 1, so that means that this a sub n coefficient has to be non-zero, and let's divide both sides through by that and solve for v sub n, so that we now have minus a1 over a sub n v1, and we're taking all of those others to the other side, meaning we now have minus a sub 2 over a sub n v sub 2 all the way down to a sub n minus 1 over a sub n v sub n minus 1. We can now write v sub n in that manner. Well, if we have v sub n written that way, we can now take this v sub n expression and replace that v sub n, so that now we only have, on the right-hand side of this expression for u, we only have vectors weighted, or vectors v sub 1 through v sub n minus 1 weighted by some scalar combination, which says then that u, therefore u, is beta 1 v1 plus beta 2 v sub 2 plus beta sub n minus 1 v sub n minus 1, where this is now a linear combination of n minus 1 vectors that is still capable of representing this arbitrary vector u that we started with. In other words, u is now in the span, or is contained in the span, of those n minus 1 vectors v1 through v sub n minus 1. And remember what we were starting with. We arbitrarily picked u. We didn't say it was a particular value. We just said, let's just pick a u that's some linear combination of v1 through v sub n. U was a completely arbitrary vector or element in this proof. And it was originally contained in the span of v1, v2, v sub n. And that allows us then to conclude that since u was arbitrarily selected, and we can now write u as living in the span of n minus 1 vectors, then that must also be equal to the span of the original n vectors v1 through v sub n. And that's what we were trying to show, that we could actually, if we have a linearly dependent list, then we can actually discard an element from that list and still retain the same span of n vectors with n minus 1 vectors. Some consequences of that linear dependence lemma are, as we said in our goals for today, two different theorems. The first theorem that we want to be familiar with is that given or in a finite dimensional vector space, the size or the number of vectors or the length of every linearly independent list of vectors is in fact as a number. So that's just the number. You just count. Let's say that somebody gives you a linearly independent list of vectors. You can count how many vectors are in that list. That's what we're referring to as the length of that linearly independent list. That numerical value is less than or equal to the length of every spanning list of vectors. Meaning if you now have a list of vectors that span the vector space, then the number of vectors in that list is bigger than the number of linearly independent vectors in that same vector space. It's greater than or equal to. Another theorem that results or is a consequence of the linear dependence lemma is that every subspace of a finite dimensional vector space, each subspace or every subspace of a finite dimensional vector space is finite dimensional. And that should be intuitive. If you now take a piece of something, and that piece could be the whole thing, or typically it's smaller than the whole thing, and the whole thing was finite, then you would think that the piece or the subspace is also finite or smaller. So now you have this result or consequence of the linear dependence lemma being every subspace of a finite dimensional vector space is itself finite dimensional. Now that we've sort of talked a lot about linear dependence, let's now get into the concept of basis vectors, and this is starting on page 39 in the third edition of Axler. Here's the definition. A basis, and so now this is really just one, and basis is the plural, B-A-S-E-S, so that means different sets of basis vectors, and maybe if you want to, you could sort of use the following mnemonic that basis, that's an I, and that means just one set of vectors that forms a basis for a vector space. A basis of a vector space V is a linearly independent list of vectors that span V. And in that definition, you can see two things that a basis has, two properties. One, the list is linearly independent. Each vector is unable to be written in terms of any of the other vectors or any linear combination of vectors in that list. And those vectors span the entire vector space V. That's what we need for a basis. They need to span the space, and the vectors need to be linearly independent. Here are some consequences of that. One is that a basis actually allows us a way to think of expressing any arbitrary vector in our vector space, or it actually provides us with a coordinate system. Let's look at then Theorem 29 in Chapter 2. And that is given this heading of criterion for a basis. Which says any element of our vector space V, so now think any vector in our vector space, any element of V is expressible as a unique linear combination of basis vectors, which is nice. Now, if I give you an arbitrary vector, there's only one way to linearly combine your basis vectors to express or create that arbitrary vector that I've been given you, or that I gave you, or that you handed me. Remember, the length of the list of basis vectors is equal to the length of the shortest possible spanning list. And to sort of see that or keep that clear, remember the following relationship relative to a set of linearly independent vectors and the spanning set. The length of a linearly independent list of vectors is less than or equal to the length or the number of vectors in a spanning list. By spanning list, we're saying the list that covers or is capable of representing any vector in our vector space. And since a basis has to have the two properties, it is both linearly independent as a list and spanning as a list. Since the basis vectors are both linearly independent and spanning, then equality must be true. And, we're talking about representing an arbitrary vector u with a unique combination of weights of basis vectors. What you also need to keep in mind, though, is that a set of basis vectors is not unique for a given vector space. Generally, there is no unique basis for a given vector space, or there are many potential or possible shortest spanning lists. Let's look at some examples so that we become or have a more intuitive feel for this concept of basis. So here are some examples. Suppose that our underlying vector space is R2, and so you could think of this as a plane, and usually we just draw it as an XY plane. Suppose now that we have this XY plane, and somebody hands us the following list of vectors. And we would like to know if given these vectors, here's v1 and here's v sub 2, indeed that is actually a list of vectors that's linearly independent. You can't represent v1 in terms of v2, and it spans the entire space. In particular, v1 is now going to be, let's say, 0 in the x and 1 in the y. So there is v1, and v sub 2 is 1 in the x and 0 in the y. And this particular this particular example of a basis for R2 is given a formal name as the standard basis, because now we have zeros in all coordinates except 1 in a unique coordinate position in each vector. Or this form of a list, this form is called the standard basis. And we can see then that we should be able to get anywhere we want in the xy plane by some linear combination of this set of vectors that form our basis, which we have now labeled v1 and v2. For example, what is the value for a1? And there's v1 plus a sub 2. There's v sub 2. So this is now vector v1, and here's vector v2. Now I've written them vertically instead of as row vectors, but now we want that to equal the point 1, 1. And you can see then that the original vectors v1 and v2 do not by themselves get you to this point 1, 1 in the original vector space or in R2. But if V1 and V2 do form a basis, then we better be able to find a linear combination of V1 and V2 that will allow us to arrive at an arbitrary point, and in this case that arbitrary point we picked was the point 1, 1. And in fact, if we simply use 1 to scale V1 and 1 to scale V2, now we have gone to the point that we wanted, 1, 1, where now our weightings, A1 was 1 and A sub 2 was 1, and that gets us to this arbitrary point of 1, 1. And if we now said let's start at the origin and go to V1, and if we scale by 1, we've gotten there, and now if we connect V2 and scale it by 1, we've now traced out a way to arrive at the point 1, 1 in our two-dimensional space by a linear combination of V1 and V2. Suppose we take another set of vectors. Let's say that now V1 is 1, 1, and V2 is minus 1, minus 3. Here's V1 and V2, where the first coordinate is the x direction, and again our underlying space is R2. That's our vector space. Here's our two-dimensional plane. And now we said that V1 is this vector 1, 1, and V sub 2 is minus 1, minus 3. And hopefully, even though my drawing is somewhat crude, you can see that those two vectors, V1 and V sub 2, are not aligned. They're not lying on top of each other, and because of that, they allow us to span the entire space, or vector space phi, which is all of R2, but unlike the previous pair, which were actually orthogonal, these two vectors are not orthogonal. They're non-orthogonal, but you don't need vectors to be orthogonal to form a basis. Meaning we can now uniquely represent any point in R2 in our vector space V by a linear combination of V1 and V sub 2. If we go back to our previous arbitrary point of 1, 1, now we want to scale V1 and scale V sub 2. And in this case, it's pretty clear that if we weight V1 with 1 and don't weight V sub 2 with 0 weight, then in fact we will get to the same point that we wanted to, which is the point 1, 1. And so now B1, B sub 2, if we drew that or represented that as a vector, it would now be this vector 1, 0, which says that we take 1 times V1 and 0 times V sub 2, and in that basis, this vector 1, 0 actually corresponds to the point in the two-dimensional space xy of 1, 1. Let's look at another example. Suppose that somebody now gives you the following list. And the list is now just a single vector. This list is in fact not a basis if our underlying vector space is R2, which we know it is because we had two coordinates in our vector, an x-coordinate and a y-coordinate. And one thing that you can see is that the length of the list, which just contains one vector, length of the list of vectors is 1, whereas the dimension, which I guess I'm getting a little bit ahead of myself, in the next lecture we will talk about or define dimension, whereas the dimension of our underlying vector space V of R2 is 2. So here you can see then that the reason that this single vector is not a basis is not because it's not linearly independent. That vector 0, 1 is definitely linearly independent, but it doesn't span all of the vector space V. If we were to look now graphically at our vector space V, which is all of R2, now we are just able to have the one vector V1. We cannot get anywhere in the x direction by a linear combination of V sub 1. That particular list then doesn't span R2. And then it should be clear that since we can't get to any x direction or x coordinate, we obviously can't get to our example point 1, 1 using linear combinations of 0, 1. What about the next list? Suppose that somebody gives us a list that's 0, 1 for V1, 1, 0 for V sub 2, and 1, 1 for V sub 3. Is or is that not a basis of R2? R2 because we have two coordinates in each of our vectors, so that's our underlying vector space. In this case, and remember what a basis is. A basis has two properties. One, your list of vectors, those vectors have to be linearly independent, and two, they need to span the space. Hopefully now you're seeing that this is not a basis of R2, and that's because it's not the smallest spanning list or the shortest length spanning list to span R2 or our vector space V. If we looked at this picture of what we now have, here's our XY. This is now our underlying vector space V. We have our now three different vectors in our list. We have V1, which is 0, 1. We have V2, which is 1, 0. And we also have V sub 3, which is 1, 1. And hopefully you can see then that we could actually rewrite, or we could express V sub 3 as a linear combination of V1 and V2 with simple weights of 1 on each, and that means then that this list or this set of vectors is actually linearly dependent. This list then is not linearly independent. Or points in R2 actually don't have unique representations as linear combinations of our three vectors, 0, 1, 1, 0, and 1, 1. Those are some examples then of what a basis might look like and what a basis is not, in terms of you need to be able to span the entire vector space, and you need a minimal list of spanning, or a minimal list of vectors that span your space, and you need that list, each vector in that list, to be linearly independent. Those two properties are necessary to have a basis. Now let's look at Theorem 31, which is now given the heading spanning list contains a basis. That means that if somebody has a vector space and they say, oh, here's a list of vectors and they span that entire space, then it's possible to extract from that list that they've given you, that's a spanning list, a set of vectors that would form a basis for that vector space. Here's Theorem 31. Every spanning list in a vector space can be reduced to a basis of the vector space. Here we're creating a basis by reduction. We're throwing things away. If somebody gives you a spanning list, then in general that spanning list may contain more vectors than you need to span the entire vector space. That's what this theorem is saying, and you can actually then identify or throw away vectors in that list that are not essential to span the entire space. So now let's look at a proof. Assume we are given a list of vectors, and we'll call that list capital B. And that list now has n vectors in it. So assume we are given a list B containing n vectors of vectors, and let's say that that list spans our vector space V, but somebody says it is not a basis. That list of n vectors, but is not a basis. Now we just have to remember what the definition of a basis was. It had two properties. One is the list of vectors needed to span the vector space, and that's what we have by this assumption. But the list also needed to be linearly independent, a set of linearly independent vectors. Well, we have the first part, that it spans V, but it's claiming that it's not a basis. And that now says then that from the definition, of basis vectors, this particular list, B, must be a linearly dependent set of vectors. And remember what we started with today. We were able to take a spanning set, and if that spanning set consisted of a linearly dependent list of vectors, we could, without reducing the ability of that new set to span the same space, we could start discarding vectors. So from before, a linearly dependent list must contain an element that is expressible as a linear combination of the other elements in the list. Which now says then that the linear dependence lemma shows that we can remove or delete this element that's a linear combination of the other elements in the list without reducing or changing the span of the list. If this new list that we've now created by removing the one element that was shown to be dependent on the other elements, if this new list is linearly independent, by removing that dependent element, we have created a basis of our vector space V, and we're done. Because we preserved the ability of that list of vectors to span the vector space, and now it's linearly independent. And those are the two properties of a list of vectors to form a basis. However, if the resulting list is still linearly dependent, we just repeat the process. We find an element that's dependent on the others and we remove it. And then we check, are the remaining vectors linearly independent? Yes, we're done. No, we look for another vector that's linearly dependent and we throw it out. So we just continue to repeat this process of reduction to allow us to create a set of basis vectors. As an example, suppose we start with one of the lists that we had done in our previous examples. Take the list that has 3 vectors in it, 0, 1, 1, 0, and 1, 1. Now we know that that set spans all of R2, and let's say that's our vector space. But we also talked about last time that because these are not linearly independent vectors in this set, it does not form a basis, but it is not a basis. Which means then that we need to go in and we need to identify one of those vectors that can be created or expressed as a linear combination of the other vectors. And if it can be, then we just remove it. In this case, this example is pretty easily cooked up. If we select the 1 vector, the 1, 1 vector, and remove it, hopefully you can see that 1, 1 can be easily represented as a linear combination of 0, 1, 1, 0. We can now remove that vector from our original list. Now we have a new list that's 0, 1, 1, 0. And in fact, that's our standard basis or standard form, and this does form a basis. Meaning we can build up a basis by reduction. If somebody gives us a spanning list, now we just need to go into that spanning list, identify vectors that are linearly dependent, and throw them out. And then we keep throwing them out until we end up with a list that still spans the same space, but now that list is linearly independent, or a set of linearly independent vectors. Another theorem. Whoops. Getting my numbers out of order. Theorem 32 in Chapter 2, which has the heading Basis of Finite Dimensional Vector Space. This says every finite dimensional vector space, we can actually find a basis for that vector space. Every finite dimensional vector space has a basis, which is nice to know. So if somebody is working with a finite dimensional vector space, it's possible to create or have a basis for that vector space. How do we show that? By definition, every finite dimensional vector space has a spanning list. That's coming to us from the definition of finite dimensional. So now if somebody says, oh, I have a finite dimensional vector space, we know that we can find a set of vectors that will span that vector space. So we now have a spanning list. And we just combine that with what we've already done as far as finding a basis by reduction. We just proved a basis can be generated or created or identified by our reduction process, identifying linearly dependent vectors and discarding them, throwing them away. So we just proved a basis can be generated from any spanning list, and if somebody gives us a finite dimensional vector space, we know that we can find a spanning list that spans that vector space. That's then the way of creating a basis, a set of basis vectors by reduction, starting out with more than we need and getting rid of what we don't need. The next way of creating a basis, a set of basis vectors, is in the other direction. And this is now Theorem 33. It's by extension, or building up. It now has the heading of linearly independent, a set of linearly independent vectors that form a list extends to a basis. This theorem now says every linearly independent list of vectors in a finite dimensional vector space can be extended to a basis. Now this is the one where we're growing a set of linearly independent vectors into a set of vectors that will eventually span the entire space. Here's our justification or proof. Given a linearly independent list again, let's call that list B, of vectors in our vector space V that are not a basis of V. So now we have a set of vectors that are linearly independent, but they don't form a basis for a vector space. A basis has to have two properties. It needs to span the space and be a set of linearly independent. This one's linearly independent, but it must not span the vector space. Here's our set V1 through V sub n. In this case, from our definition of a basis, we know we're missing the other part, or piece. From the definition of basis, if B is linearly independent in terms of a list, then it must not be satisfying the property of spanning the vector space. So B must not span our vector space V. If that's the case, then let's select another vector or an element in our vector space V. Select an element in V, let's say that's U, element of V, such that this new element is not contained in the span of our originally assumed set of linearly independent vectors, or our list of linearly independent vectors, which we were labeling as B. Now what we want to do is form a linear combination to create U, meaning we can add up all of the linearly independent vectors that we started with, v1 through v sub n in our set B, and add to that whatever we need in the vector space V to yield our vector U. This is just a linear relationship, so we can actually use that to solve for Q that's needed to be added to v1 through v sub n to create this arbitrary vector U that's not in the span of V. Now Q is equal to U minus V1 minus V2 minus V sub n. And look at the right-hand side. U was in our vector space, as are all of the vectors V1 through V sub n, which now says that V is an element of our vector space because one of the properties of a vector space is that it's closed under addition. And that's all we're doing with the vectors on the right-hand side, is we're just adding them up. Well, if Q is in our vector space V and it's independent of V1 through V sub n, let's just augment our original list B and form a new list. And sort of like we're doing an iterative process, let's add Q to the list B, and we're sort of doing this like we might be programming. Now we're saying B, a new B, is going to be the old B, V1, V2, V sub n, in addition to Q. And now we need to look at this new list. Now we have n plus 1 vectors in B. If B now spans our vector space, this new list of vectors v1 through v sub n and q now forms a basis, because q was linearly independent of v1 through v sub n, and it's now increased the ability of this new set of n plus 1 vectors to span a part of our vector space V. And if it spans all of V, then it forms a basis. It's a basis of our vector space V, and we are done. And like before, if it's not quite what we need, if B does not span our underlying vector space V, then we simply repeat the process. We identify a new vector, U, that's not contained in the span of B, and we can now find a new Q that allows us to generate, as a linear combination of vectors, that U, and then that Q gets added into B, and we just keep going. Let's look at an example. Where now we're building a basis. We're now doing it by extension, building a basis from a linearly independent set of vectors. Suppose we start with B, and now I'm going to form these vectors as columns. Now we have x, y, z, let's say, as our coordinates, and the first vector is 1 in the x direction. The second vector is 1 in the y direction. And let's have our vector space being R3. Now this is the world that we live in, this three-dimensional space. Suppose now, well, it's clear, I hope, that B, those vectors are linearly independent. They're in orthogonal directions, actually. We're going in the x direction, we're going in the y direction. But they don't span all of R3 because there's no way that we can get outside the xy plane. If we think of the tabletop, then we're just stuck on the tabletop and we can't move up or down because we do not have a vector in our set B that has a component in the third dimension or in the third coordinate or in the z direction. So let's now find a vector u that's not in the span of B, and let me just arbitrarily say, well, 5, 6, 8 cannot be expressed as a linear combination of those two vectors, v1 and v sub 2. Hopefully it's clear then that this choice of u is such that u is not contained in the span of B. Now we can take u, which is 5, 6, and 8, and form a sum of the original vectors in B, v1 and v2, plus some new vector q, and we can now solve for q by pulling or pushing the v1 and v2 to the other side. We now have q1, q2, q3. That's now 5, 6, and 8 minus v1 and minus v2. And now we have 5 minus 1 or 4, 6 minus 1 or 5, and 8 minus nothing or 8. And our q now is 4, 5, 8. We can now create or add that q to our original list, and we now have created a new spanning list, which we're going to go ahead and relabel as B. And now B is a list of one more vector than we started with. It's now v1, v2, and now it's this q, 4, 5, 8. And in fact, this particular list now is a list of linearly independent vectors, and it does span all of R3. And so this particular B has now been extended to allow us to form a basis for our underlying vector space V, which is the three-dimensional space R3. What we now want to do is start talking about dimension now that we have these different ways of spanning and forming sets of basis vectors. We know about linearly independent vectors. We know about linearly dependent vectors. We now can start talking about or quantizing or quantifying the number of vectors in a list, and that's what's going to allow us to speak of dimensions of finite dimensional vector spaces.